Hello, everyone. My name is Xiaoming Chan. I'm a PhD student from University of Phoenix. I'm glad to be here to talk about our recent research work. And the topic is Fed-GBM, or cost-effective federated gradient boosting tree for non-intrusive load monitoring. Today, we're going to go through the several parts. First, I will introduce the background and motivation, followed by the methodology and the implementation. And I will show the experiment and readout analysis. Last, I will talk about the conclusion of future work. Now let's get started with the background and motivation. The appliance level energy consumption is very important for sustainable energy consumption, scheduling, and it supports to reduce the electricity bills at user end. Non-intrusive load monitoring, also called NIL, is a computational method to identify appliance status and extract the appliance level power consumption from the main ratings. As the aggregated, the main ratings is only monitored at the single central point. It avoids high expense of sensor installation and maintenance. Here are 5 existing techniques for a NIL problem. That include this graph signal processing, factorial hidden markov model, recurrent neural network, convolutional neural networks, and the sequence point learning paradigm. It's widely used for the NIL application. Although these techniques show the success in NIL problem, there are still several challenges in real applications. First, most existing solutions impose a high computation and storage overhead due to the complex structure and a large amount of model parameters. And second, the data is limited for model trainings at the user end. As the user cannot get enough data to do the model training, so the quality of the model cannot be guaranteed. Third, the traditional centralized model training leads to privacy concerns and expensive data transmission. And also, the existing collaborative training approaches highly depend on encryption and differential privacy techniques. These techniques also bring the extra computation cost. Last, communication efficiency is now well studied in recent collaborative solutions. To address such challenges, we propose the cost-effective collaborative training framework called Fed-GBM. We use the gradient boosting decision tree as a base model. By working with a sequence point learning method, the great GPT model can reach state-of-the-art skill accuracy for NIL. It supports to reduce the computational complexity compared with the neural networks. Also, our framework achieves the horizontal parallel learning. In horizontal parallel learning, the data is managed by the different owners, and the training checks are distributed across the multiple participants, and the local trained models parameters are periodically aggregated by a master node. So by using such learning paradigm, we can train a model without exposing the raw data. Now let me briefly introduce the Fed-GBM. Our framework contains 2 roles, the server and local runners. The server is used as a synchronization controller to coordinate all the local runners to jointly train the model. For the local runner, it represents a wide range of the computation devices with the limited resources. The data is managed by local runners. The workflow of Fed-GBM contains 6 phases. First, the local runners jointly create the preset context scratches for different features. and randomly initialize the prediction values for the local samples. Second, initialize a new tree. The root of the new tree is first pushed into the queue and set to active. Third, build the histogram. In this phase, for a given node, each local runners use the first order and second order gradients to build a histogram. In the first phase, I just want to find a split. We apply the two-stage voting scheme to find the best split point for active nodes, and then broadcast the results to the local runners. When the local runners receive the results from the server, it will apply the split. If a stopping criterion is made, the nodes stop the growth and becomes a leaf. After we finish this server phase, the model is produced. Now let me show you the details about the two-stage voting scheme for the GBM. The two-stage voting is developed for reducing the communication cost when we want to find the best split point. There are three stages in such scheme. First, the voting at the local runners. In this stage, all the features and corresponding split threshold are iteratively evaluated, and the runners select the top K candidate features according to the maximum gain. Second, voting at the server. In this stage, the server selects the list of beta K candidate features by using the majority voting. And last, once the local runners receive the candidate feature results from the server, it will send histograms about the candidate features. The server will aggregate the histogram of same features to a global one, and then will perform the global split voting. By using such two-stage voting scheme, we have two benefits. First, communication cost is not linear with the number of features and only depends on the value of K. And the second, only the histogram of the K features are uploaded to the server, and it is challenging to recover the set raw data from the histograms. So the risk of proxy leakage is significantly relieved. We also provide the probability bond for selecting the best split features. According to the bond, we can figure out the three key factors impacting the model performance. They are a local data size, voting size, and a local random number. Because the workload of the split data is small and the available CPU cores cannot fully utilize at both the local runners and the server to avoid the waste of computation resources, we proposed a node-level parallelism scheme for node growth to increase the computation efficiency. We first theoretically proved the resource allocation in such scheme is the online time non-clairvoyance problem. We characterize the node parallelism problems as follows. First, in our system, there are executors with an identical resource running in parallel at the runners and server. The jobs of node split are assigned among these executors for processing. The job is released only after its parent job is finished. Last, the scheduler has no information about the processing time of the job. We identify the problem by proposing the theorem as follows. Because for the non-online time scheduling problem, the list of scheduling algorithm can achieve the best competitive ratios. So we choose the list of scheduling in our work. To evaluate the performance of framework, we implemented prototype and conducted the experiment on two open access the data sets, the REDD and refit. We deployed the Fed-GBM framework and scalable distributed disk target cluster. Each computation nodes can be regarded as the local runners. They are connected to a powerful EC2 server. The EC2 server coordinates different workers to train a unified GPT model according to our design. The configurations is showing in the slides. We also provide the hyperparameters for the training the GPT. Our experiment evaluate the Fed-GBM from 3 aspects, including convergence, accuracy, and communication efficiency. For the convergence, we can see in the figure, the training loss drops with the increase of the boost round. The convergence rate of the individual house is similar to the overall one. And most importantly, the Fed-GBM guarantees a good convergence regardless to the appliance type, appliance number, and residential environment. We also compare the performance of Fed-GBM without the two methods and two data sets. According to the results in the table, the centrally trained models often achieve the better performance, but the locally trained ones always shows the worst performance. This is because the centrally training method can easily extract the sufficient knowledge by using the full pop data. The high generalization ability can be guaranteed. The Fed-GBM models, let's looking at the Fed-GBM models. It outperform the locally trained ones. They provide a close approximations of the MAE to the centrally trained method and also prevent information leakage from individual power users. Also, some Fed-GBM models achieve lower SAE or NDE values than the centrally ones, such as in the case of dishwasher and the kettle in the refit. It means the Fed-GBM sometimes provide a better estimation of total energy consumption. It helps to avoid outlier estimates. We also carefully evaluate the communication efficiency of the Fed-GBM by comparing with another state-of-the-art framework called the Federate. To make a fair comparison, so the algorithms, those algorithms are deployed on the same network settings. We monitor the outgoing traffic of each local runners. The combined outgoing traffic of Federate is more than 2 times of Fed-GBM. The communication cost of each runner shows the same result. Also, the Fed-GBM remains the stable communication cost since the outgoing traffic varies within a narrow range. Instead, the Federate shows a significant variance in the communication cost. To better understand the impact of the K values for Fed-GBM, we also do the model trainings with the different K values. on 5 selected appliances. From the experiment, we know the convergence of Fed-GBM is not sensitive to decay, and the time cost of the model training rise with the increase of decay value. There's no linear correlation with the MAE and MK. The third, the communication cost of Fed-GBM is proportional to the K, but it's not over the Fed-GBM. These results are aligned with our theoretical expectations. Now, for the conclusion, the Fed-GBM addressed the low model fitting due to the limited data scale in NELM applications. And two-stage voting scheme realize the communication cost reduction and provide privacy protection. And node parallelism for node growth is also implemented based on our online scheduling algorithm. It's helped improve the result utilization. Also, we still have several challenges in our future works. First, at the node level parallelism on the leaf-wise model is not well studied. Second, we will also explore a location where decentralized training architecture to avoid expensive communication overheads with end server. And finally, we are going to integrate asynchronous training strategy to apply to help our framework apply in the more complex environment with heterogeneous devices. Thanks you for listening.